Today we are going to talk about two-dimensional collisions. Yes. If you're listening to this at home, I apologize. All right. So first thing we're going to do is we're going to review basic collisions and what's going on when two objects collide. We did one-dimensional collisions the other day. So if you have just a particle in space, just a generic particle and another particle in space, and we're going to say, and they collided along this straight line, this axis like this, right? We call this the x-axis. So they had mass. So we'll call this M1 and M2. And maybe this guy was moving like this, and this guy was moving over here. So this has V1 initial, V2 initial. And so they came together, and these could be anything from protons to black holes to whatever, and to galaxies even. They're going to come together, they're going to interact in some way, and then maybe they fly apart. So let's, so afterwards, during the collision, here's object 1 and object 2. They don't have to be the same size, but they apply forces to each other. So when they hit, this is the force of object 1 on object 2. And this is the force of object 2 on object 1. And those forces are equal and opposite. Who said that? Newton. That was his third law. That for every force on one object, there must exist an equal and opposite force on another object. Okay, so that's a law of nature. So this must happen. And these forces are applying at the same time. They're going, bam, right? The duration of time of these forces is the same. So we'll just call these average forces, and so we'll call this an interval of time. So the time that this force is applied here is the same as this is applied here. So we had F21 times delta t equals F12 times delta t. But they are equal, but in the opposite direction. That is, F2 on 1 is in the negative direction of F1 on 2 times the same time. Well, we have the impulse momentum theorem. If you have a force times a period of time, that we showed that to be equal to the change in momentum of the object. So really, this represents the change in momentum of object 1. So object 1 gets its momentum changed. That's equal and opposite to the change in momentum of object 2. Object 2 gets its momentum changed. Okay, so yes, during a collision, an object gets its momentum changed. Another object gets its momentum changed. But when you add the two momentums together, the two changes in momentum, add this to the other side, you get 0. And what this means is that if I make this my system, these two objects, and there's no forces from the outside of this artificial boundary that defines my system, if there's no net outside force acting, then the momentum of the system doesn't change. It's conserved. Look how simple this is. Really, these ideas are not that complex. And yet you get one of the most, out of it emerges one of the most profound ideas in physics. That if no net outside force is acting on your system, the total momentum, the initial momentum of your system will be equal to the final momentum of your entire system. So that's what we did last time, where we said, hey, momentum is conserved during a collision, assuming you have a closed isolated system. Closed means we're not adding or subtracting any mass from our system. Isolated means there are no outside forces, net outside forces acting. You can have an outside force acting, like if these were two billiard balls hitting, and you put a billiard ball table right here, right? So let's say this is the table, and you say, well, what about gravity? Yeah, gravity is pulling this down, m1 times g, but what else is acting on it? A normal force, we'll call that n1, and these two forces cancel each other out. So these two forces, because they cancel out, there's no net outside force acting. And so these two forces do not change the momentum of this ball. Only the interaction between the two balls will change the momentum. Any questions on that? Okay. Well, now we're going to apply this situation in 2 dimensions. And it's the same thing, it's just now it's more complicated. And, I mean, because now we have an x direction and a y direction. So suppose that these two objects, here's object 1, here's object 2, and suppose this object is moving in this direction. Look how fast it's going. Okay, so this is m1, and this is v1 initial. Here's v2 initial. Here's for m2. But now, you know, they're not quite on the same line, so that when they interact, here's 1 and here's 2. Here's the moment of collision. The force does not line up with their initial motion. The force is at an angle like this. So this is, boom, F1 on 2 equal and opposite F2 on 1. And again, they apply for the same amount of time. So this is the change in momentum of object 1. This is the change in momentum of object 2. And they are in equal and opposite directions. But now, these changes in momentum are acting both in the x and y direction. They're in 2 dimensions. And so, I can look at this in the x direction. Here's the x component, and here's the y component of the change in momentum of object 1. And here's the y component, and here's the x component of the change in momentum of object 2. And this change in momentum and this change in momentum are equal and opposite. And this change in momentum and the x and the y's are both equal and opposite. Zoom in a little bit. Okay? Which means that we're going to be able to do this. So what we can do is say that the change in momentum in the x direction, well, hold on a second. The initial momentum in the x direction is got to be equal to the final momentum in the x direction. So you can treat the x direction completely separate. And the initial momentum in the y direction equals the final momentum in the y direction. So now it's just twice as complicated. You have this equation and this equation. Now what do you have to know? You have to be able to know what the angles are. Like if these two objects hit each other and come off at angles, you would use those measured angles to figure out what the components of the momentum, the x and y components are. Okay, so let's take a look at this situation. Let's define this to be positive x and this to be positive y. Looking at our example here, well, in the x direction, I would look at, okay, this is M1 V1 initial plus M2 V2 initial. Okay? Because both of these velocities are in the x direction. This one's negative. This one would be negative if I gave it a value. And you can say this is all in the I hat direction, right? Make it a vector. But what about the y direction? If I look at this problem, what's the initial momentum in the y direction? Zero. You look at these two objects, the way I've drawn them, the way I've selected my axis system. Neither one of them are moving in the y direction at all. So there isn't any momentum in the y direction before the collision. Well, what does that mean? That means the final momentum in the y direction will also be equal to 0. Okay? Which gives you information. You can take this component and set it equal to this component and do it. So you would say, looking at the final momentum, you would say M1 V1, and then you could go sine theta 1 final. That's the V1 final. There's a lot of annoying subscripts when you're doing collision problems. You have initial and final, you have object 1 and object 2 to keep track of. So you have to use a lot of subscripts. Plus M2 V2 final times sine theta 2. This is the momentum of this, of this, and this is the momentum of this. It has to equal 0. This gives me an equation where I can solve problems. Now in the x direction, I would have M1 V1 initial in the x, well, we want to put it in the x direction, so we'll do cosine theta 1 plus M2 V2 initial cosine theta 1. Oh, these are the initial angles, equals, oh gosh, M1 V1 final cosine theta final plus I'm off screen. Nope, I'm not. M2 V2 final cosine theta final. This is for object 1, this is for object 2. So I mean, there's a lot of complicated stuff here, but look, this is just the initial momentum of object 1 in the x direction, the initial momentum of object 2 in the x direction. You add them up. That's what this is saying. Equals, well, this is after the collision, and you'll be given all the information you need in a problem. And then it's just a matter of using algebra 1 to figure out what the angles are, or what the final velocity is, or whatnot. Okay, so really, if you know that how to take a vector, momentum vector, and break it up into its x and y components, which you all know how to do. This is pretty easy stuff. You know, that's just... Now, there is one really, really cool example of this, and I want you to follow along. I want you to take out two identical coins. I have 2 quarters I'm going to use. This is a, we're going to make 2 assumptions for this example. Okay, first, I'm going to take these 2 quarters, and I'm going to call this, oh, now if I was a good teacher, I would have put a little, I'm going to call this, I don't know if it'll show up. This will be quarter 1. Does that show up? No, not really. And this will be quarter, oh, I know what I'll do. This will be heads. That'll be tails. That doesn't show up very well either. But anyway, it doesn't matter. Okay, we're going to assume that M1 equals M2. These 2 quarters have the same mass. Okay, and we're going to assume that V2, well, I can write it over here. V2 initial equals 0. In other words, this one is going to stay at rest. Okay, and we're going to assume that we have a an elastic collision. Now, it's not going to be an elastic collision. It's just going to be really close. I mean, when these 2 quarters, I'm going to collide them, and they make a little clink noise, right? If they make noise, some of the kinetic energy is going to be lost to the environment. So it's not going to be perfect, but it's going to be really close. An elastic collision. All right, so then what I'm going to do is this. I'm going to take this quarter. Now, I rehearsed this earlier, and it actually kind of worked. That doesn't mean it's going to work when I'm recording, obviously. So this is going to be the initial position of object 2. And what I'm going to do is I'm going to slide this and they're going to collide. Okay? It's going to be really exciting. Whew, look at that. So let's do that again. This is a 1D collision. Whoops, let's do it a little harder. So if I were to do this in slow motion, these are the same mass. So this one comes together like this, hits it, and transfers all its momentum to the other one. If these were perfectly elastic, we could show that what would happen is that this would stop right here and transfer all its momentum to the other quarter. But what happens if I hit it at an angle? Now I'm going to do this a few times until I really get it right. All right, so I want to hit it harder than that. Nope. Yeah, I guess that's I'm not going to do much better than that. Who did that?
That was Kyle.
Kyle? Kyle. I'm trying to teach a class, and what does he do? All right. So these are the final positions. So here's, this is quarter 2. And if I draw the center of this, here's the center, roughly the center, and here's roughly the center. Oh, could you get me a protractor out of the... this was the path that this took. Now, if I had frictionless paper, right? Thank you. If I had frictionless paper, This would just go off like that. Now let's make an estimate here. When this quarter hit this, it was probably right about here. So I'm going to draw, this is the point of collision. So this is 1, and here's 1. So if I draw this, and again, I'm trying to do this for real, so it's not going to be perfect. But if it was perfect, this would come off a little bit more. I want to do some analysis on what this angle should be if it was an elastic collision. So, the initial momentum equals the final momentum. Am I still on screen? Yeah, okay. Well, what was the initial momentum of the system? M1 V1 initial. Okay? Now, what was V final? What is P final? What's the final momentum? Well, you have this momentum and you have this momentum. And this came off at a certain angle. And if I add these two momentum together, I should get this. So here was object 2's momentum after the collision. Oh, 2. After the collision. And then if I pick this momentum up and then put it here, I'm just adding them together. Okay. So what I did is I said, okay, initial momentum equals the final momentum. Well, here's the initial momentum. Here's the final momentum is the sum of M2 V2 M1 final M1 V1 final. I just added the two momentum together. Everybody with me? I know this is kind of excruciating. All right. So I'm going to write this now as a vector equation. M2 V2 final plus M1 V1 final equals M1 V1 initial. But what's the same? Yeah, these masses are the same. So what, M1 equals M2. So what can I do? Yeah. I'm going to cancel them out. Just divide both sides by the mass. Now, what is this? This is a triangle. This is a vector equation, and that I've drawn up here. But this doesn't say anything about the angles. But if I assume that we have an elastic collision, well, what does an elastic collision say? Well, the initial kinetic energy equals the final kinetic energy. That's what elastic means. We don't lose any kinetic energy. Well, what's the initial kinetic energy? 1/2 M1 V1 initial squared. And remember, V2 was at rest, so it didn't have any kinetic energy. Equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Okay? Right, this is the total kinetic energy after the collision equals the total kinetic energy you had before the collision. Now what goes away? And the 1/2. So I have this. V1 initial squared equals V1 final squared plus V2 final squared. So if I come up and look at my triangle, I can just cancel out the mass. So I'm just going to cancel out the mass. So here's V2 final, V1 final equals M1 initial. So this tells us how to add them together, and that allows us to draw the triangle. But look, this V1 final, that's this leg. V2 final, that's this leg. And V1 initial is this leg. So what's the only kind of triangle where this squared plus this squared equals this squared? A right triangle. Which means this has to be a 90-degree angle. Which means this, here's V2 final, here's V1 final. These two vectors should form a 90-degree angle. Did they?
Almost.
Not really. If I put this, I don't know, where would they meet? I'm just going to draw a little hand sketch. It's about a little over 70 degrees. Okay, so it wasn't really a very good. What does do this really well, even better than quarters, though, is billiard balls. And I would use billiard balls to do this, but they don't fit very well under the document camera. All right. Quarters fit better. So here's a really nifty little application. So if you're playing pool, have you ever scratched the cue ball into the corner pocket? Yeah, because the ball was right in the middle of the table and you hit it and they both went in. They're coming off at 90 degrees, or really close to 90 degrees, probably like 85 degrees, because billiard balls are really good. That'll help your pool ball game. Also, shuffleboard. Have any of you played shuffleboard? Yeah. Yeah, admit it. Shuffleboard's not just for the old people. Shuffleboard is fun. So, and other games like that. So but this is kind of cool. If you make these assumptions, the masses are equal, one of the objects is at rest, and they have an elastic collision, those two objects will come off at 90-degree angles. They have to. Okay. So just to summarize, if you have a two-dimensional collision, the analysis of before and after, you can split up the x and y components of the momentum, treat them as separate problems, but you'll have to be given the angles that they come off after the collision to apply in there. Get your x and y components of those momentum vectors before and after. Of course, you might have to solve for those angles based on what's given. Any questions? Okay. That is all.